So starting with the part two of the lecture about the artificial neural network. So let's move to the next slide. So if we look at this one, non-linearly separable data. So in case if your data is non-linear, so how to deal with that one? This is also a challenge for it. And and perceptron learning algorithm will fail definitely because no linear hyperplane can separate the data perfectly, right? So by this way there is some challenges for that one. If you look at here and look at the XOR operations over here, that how this XOR means exclusive OR. Okay, so when there is one, okay, so it means that if any of x or x2 is 1, okay, it will be 1, right? Okay, if anyone or I could just reformulate that if this is similar values, okay, similar, this is like an easy way to learn. If it is similar, okay, so in usually in exclusive or it is 0, but here is a sign function, so so what we do it, so it becomes -1, okay, and here also -1. So for similar is -1, and for dissimilar values, like for example, this is 1, 0 and 0, 1, we have 1, right? So this is just like a simple trick for you. Okay, now let's explore multi-layer neural networks. So multi-layer neural network is very interesting, and you see that there are two way of learning. One is called feed-forward neural networks learning, and one is called backward learning neural network. Okay, so in the forward learning network, okay, what happens for example, this is your input layer and there is many headers layer, right? This is many headers layer. It could be one layer, two layers, three layers, more than one layers, and up to n layer, right? So we call as an n layer, right? And this is your input, right? And this is your output, right? Okay, so if your algorithm is learning like this direction, we call it feed forward. So every layer is giving a feedback to the next layer, and it is removing the error, reducing the errors, and the learning rate is higher. So if the learning rate is 0, so you stop over there, right? Okay, now if you are going on the back direction, so this called uh, backward neural network learning, right? So now see that I will show you both example, and then we will see that how we learn from it. So multi-layer neural networks with at least one hidden layer can solve any type of classification task, even involving non-linear decision services as well, right? So look at this one. So there are hidden layers, right? And as I explained earlier, how it looks with exclusive OR data. So with the blue lines, you can see the blue line is your input and output, and the red line is your hidden layers, right? So with the hidden layers, you find your output. Now this is another classification via multiple layers, right? Multiple layers has many features, as you can see from this one, and that layers, number of layers here, these number of layers, these are called the depth of the layer, right? So if the number of layers is 10, so the usually the depth is considered to be the 10th. So here you see over here we starting from layer 0, which is the first layer, which is sometimes we don't count it, right? And then we go for layer L layer, right? So usually we start from 0, and we end up with the we start, so if you see over here, we start with the 0 and we end up with the L layer, right? And there is a very, very important terminology which is called activation function. As I already told you that this is very important to activate the next layer, right? So if there is no learning, right, and if the y minus y lambda is 0, there's no learning. If the previous value is same like the new value, so you stop over there, and there your function deactivates, right? So but if this one is if there is a learning over there, this function get activates and feed forward the new values, okay, and you get the more learning over there. Okay, so so every layer is give you a different activation value, right? And here is a like linear predictor. Now look at here, activation function. So yeah, we have like various kind of activation functions. Some are like might be you have studied in operation research. Some like some are linear functions, that how the linear function looks like. Here is like sigmoid functions, like which is starting from 0 to 1. So maximum value is 1 and minimum is 0, right? And it looks like a S shape, right? So and there we have like 10 h functions, right? So here it starts like from like it is between the +1 and the -1 values, right? It look like s, but it is a little bit different from the normal sigmoid functions, right? And there is a sine function which is mostly kind of discrete, or I can say it's a digital. So it is either -1 or it's like either positive, right? So sine function is like variates at 0 level. Okay, so now look at this one. The next slide, we if you go over there, and the function is written on the right hand side, right? So you can easily compute the values and you will get the this kind of function, or you can plot it by using Python plot functions, metaploid functions. Okay, now learning multiple layer neural network. Can we apply like question perceptron learning rule to each node, including the hidden nodes? So like these kind of questions like neural network is asking to you, right? And what about like the error? As I told you that if the error is 0, you stop over there, right? So if the new value minus the old value is 0, right, then you stop over here. If it is greater, then you add the new values, you add the weights over there, you increase it. If it is less than, then you minus it. Okay, so approximate error in the hidden nodes by the error in the output nodes. So problem, what are the problems? Not clear how adjustment in the hidden nodes affect overall error. No guarantee of conversions to the optimal solution, right? So conversion is means that when it is 0, when you're like y minus y lambda is 0. Now look at their like gradient descent is an optimizations algorithm in the ANN, and it finds your loss function, that how much information is being lost over there, and it is also to measure the error across the training point. So every layer you find that how much information is being lost over there. One thing you need to know that like while training it takes a lot of time, while testing it takes less time. So what we do, we use the GPUs, like high performance computing or graphical processing unit we call it. And you can use your own local GPUs to train your model, artificial neural network, or you can like hire it online GPUs using the Kaggle or some other platforms. So as I told you, lambda, this is called lambda. As I told you before, you should keep in mind that lambda is like learning rate, right? Mm. Now we switch to the next slide and see that what are the other important factors. Okay, SGD is a very also important, like optimization algorithm, and it is based on probabilistic value, because if you look at the stochastic is mostly like working on the probability, right? And update the weight for every instance, how to update it. So that is the power of SGD, right? Okay, now let's see. These are different available options with us. Okay, computing gradients is also another, like how to compute the gradients. Okay, gradients is, I would just like similarize with the regression function. In the regression function, we have like slopes, right? So here also we have gradients, that how gradients was to optimize the overall functions. Okay, so this one is the back propagation. As earlier I told you that one is a feed forward and another is a back propagation algorithm. So like here it works in a reverse way, rather than the feed forward. And these are like what are the output layer, how we define our output layer. So this formula is used for the output layer, right? For the hidden layer, like this formula is used, right? So look at this one. Gradient at layer 1 can be computed using the gradient at layer 1 plus L plus 1, right? And start from layer L and back propagate gradient to all previous layers. So you go back and check where is the problems, right? And use gradient descendant to update weights at every epoch. So at every epoch means like your full iterations, you check that where is the problem. And for next epoch, what you see, use the updated weights, right? You check the updated weights to compute the loss function, that where how much loss of information is done, and its gradient, right? So so then iterate until the convergence, right? Okay, so convergence means I told you when there is like no more learning, so y minus y lambda is 0, right? So number of nodes in the input layer, one input node per binary continuous attributes. Okay. So issues, what are the different issues? Definitely, ANN, every algorithm has like, issues like in classification, we have by the trees over there, binary trees and normal trees, they have their own limitations and issues. Similarly, like ANN has its own issues and um, the attached shortcomings, I would say, like that one. So number of hidden layers and nodes per layer, initial weights and biases, these are like we need to know about that one. Learning rate is important thing. Maximum number of epochs, how many epochs we need to do so that we stop for the next layer. And minimum batch size of the minimum batch SGD, stochastic way, probabilistic way, right? So these are like either the input should be binary or continuous, right? And also for k or log of k nodes for each categorical attribute with the k value. So how these like number of nodes, it can be like to know about that one, this is the most important thing. And the number of nodes at output layer, right? These are two most important thing. No, characteristics means that what are the important things in the ANN. So as we told that multi-layer ANN are universal approximators, means like they can like find anything, but could suffer from overfitting. So in the previous class we talked about overfitting. What is overfitting? And I show you some graphs that overfitting is also when your prediction is not like up to your desired. So if the network is too large, so in that case the overfitting can occur. Naturally represent a hierarchy of feature at multiple levels of abstraction. Okay. Okay. So sometime gradient descent may converge to the local minimum. Okay. So it will not give you the optimal values. Okay. Model building is compute intensive, but testing is fast. As I told you that this is a very important point that mm, that like if you want to compute the model, right, computation is intense, you need a GPUs for that one. So I would write for you, we need a GPU, right, for that one, GPU. Okay, but testing is easier, so you don't need a GPU, you can do easily. Can handle like redundant and irrelevant attributes because weights are automatically learned for all attributes, right? So it means this is a good thing in this ANN is that it can handle redundant means which is repeating and irrelevant attributes as well. Attributes means the usually in normal classification we call it columns, right? But here attributes means the inputs. So sensitive to the noise in training. Yeah, noise like this ANN is sensitive to the noise. If the noise is added, so the results may vary. It may different, right? This issue can be addressed by incorporating model complexity in the loss function. So yeah, so if you want to fix this one, so we have to use the loss function, and through loss function we can remove the noise. Okay, so difficult to handling the missing attributes. If the attributes are missing, some variables are missing, then